Module number 3 was very much about quadratic equations, and our exponents maxed out at 2. Starting with Module 4, we're going to be doing a lot more exponent problems, and we're going to go beyond exponents of 2, so you're going to see exponents of 3 and 4 and perhaps even more. We have a lot of definitions in this first lesson. First definition is what a power function is, and a power function is any function in the form of f of x equals ax to the n power, where a and n are non-zero real numbers. So a is that same a that you've seen before from the quadratic equations, and n means it can be any exponent as long as it is a non-zero real number. It means it can't be 0 and it must be a real number. For power functions, the a is referred to as the leading coefficient. So the leading coefficient is the first coefficient you see, assuming that is in descending order of exponents. And n is referred to as the degree, which is the value of the exponent. N is going to be the highest exponent that you see in any of these power functions or the upcoming polynomial functions. A power function with a positive integer n is called a monomial function. Monomial is actually a term I've used in the past, and what it just simply means is it is a single term, a function that is a single term, meaning there is no addition or subtraction involved. It is all multiplication. First thing we're going to talk about is what is the end behavior of a function, or the end behavior of a graph. And an end behavior is how a function increases or decreases as it approaches infinity or negative infinity. So I've got a couple of graphs down here. The one on the left is a line, just a straight line. And we know lines go on forever. They go forever to the right and they go forever to the left. And that's why we oftentimes say that the domain of a line is all real numbers. But also notice that as the graph goes to the right, so as this graph is going to the right, it is also increasing. And as it goes to the left, it is decreasing. So how it is going to the right and to the left, and whether it is increasing or decreasing, is referred to as the end behavior. This first graph, if we want to describe the end behavior, notice that as the graph goes to the left, so as we're moving to the left, it is going downward. So we would say that this graph is decreasing to the left. But as the same graph is moving to the right, as this line is moving to the right, it is going up, which means it is increasing to the right. Looking at the graph on the right, we have a parabola, and notice the parabola is going downward on both the left side and the right side, this being the left side and this being the right side. So that means that this graph is decreasing, since it's going downward, both left and right. So decreases both left and right. This is how we would describe the end behavior. There are some patterns to end behavior. The patterns has to do with the degree of the function, and it has to do with what the leading coefficient is. So looking at this chart, when we look at the degree of a function, we're looking to determine whether the degree is an even number or an odd number. Remember, the degree means what is the exponent, what is the highest exponent. And then when we look at the leading coefficient, we're looking to see whether the leading coefficient is a positive number or a negative number. So let's say, for example, we have a parabola. And we have a parabola, and we know it's a parabola because it has an even degree and it is a positive leading coefficient. So that means that maybe the graph is in the form of y equals, the leading coefficient is a positive number, so let's say it's a positive 3. And then, since the degree is even, maybe it's an exponent of 2. The 2 is being an even number. So y equals 3x squared. That would be a graph that looks something like this. where it increases on both sides. So, and it actually, any term with a positive leading coefficient and an even degree is going to increase both right and left. So it doesn't matter whether it has an exponent of 2 or an exponent of 4 or an exponent of 6, as long as the exponent is even and the leading coefficient is positive, it will increase on both right and the left. But let's say we have an odd degree, but still have a positive lead coefficient. So an odd degree with a positive lead coefficient might be, and I'm going to use function notation this time, f of x equals 2x to the third power. So that is an odd degree, so the exponent is odd, and the leading coefficient is a 2, but it is a positive 2. That graph actually looks something like this. We're going to be exploring these graphs at great detail later on in this chapter, but it's sort of an S shape right there. And notice that when it has an odd degree and a positive leading coefficient, then on the right side of the graph it is increasing, but on the left side of the graph it is decreasing. So we would describe the end behavior as decreases left, but it is increasing on the right. And then what happens if we have negative leading coefficient? So let's say we have a even degree, but a negative leading coefficient. Well, I'll go ahead and use one that we're familiar with. And one we're familiar with is actually another parabola. So maybe our function is f of x equals negative 2x squared. So that is a negative leading coefficient, so the leading coefficient is right there and it's negative, and the degree is even. That means the exponent is even, and we know from the previous chapter that that graph would look something like this. It is an upside down parabola, and being an upside down parabola, it is decreasing both left and right. So decreases both left and right. And then finally, let's say we have an odd degree, but a negative leading coefficient. So an odd degree with a negative leading coefficient might be negative 1, and we don't need the negative 1 there if it's a coefficient. So maybe it's just negative x to the third power. So that would be a negative 1 as the leading coefficient, and x to the third power is an odd degree. That graph is going to look something like this. It's an S shape, but it actually does the opposite as the one we have above it because the leading coefficient is a negative number. So we would say this one is going to increase to the left, but it decreases right. So let's look at some examples. Example 1, describe the end behavior of f of x equals negative 2x cubed using the leading coefficient and degree, and also state the domain and the range. So let me put my chart back up here. And what do we have? We have a negative leading coefficient. Here's the leading coefficient. It's this negative 2. And then we have an odd degree. The degree is 3. So when you have a negative leading coefficient and an odd degree, going back to our chart, negative leading coefficient and odd degree is going to be the box in the lower right-hand corner. And that means we are going to have end behaviors of increases left and decreases right. So that's how you would describe it. Write out increases left, decreases right. And then it also says find the domain and the range. These power functions will all have the same domain. They do expand forever. There's no limit to any number you can plug in for x in the real number system. So the domain of these power functions is going to be all real numbers. The range is going to be a little bit different. So again, we've not explored what negative 2x to the third power looks like. So I'm going to go ahead and put this as a graph on Desmos. And here's the graph of y equals negative 2x to the third power. And you can see that as we zoom out, we can see that it is increasing forever to the left, but it is also decreasing forever to the right. And that means that the range is also going to be all real numbers. Hopefully that makes sense that it's going to be all real numbers, because if it increases to the left and decreases to the right, it's going to touch every y value in existence. So the range on this one is all real numbers. Let's do the next one. The next one is describe the end behavior, domain, and range of f of x equals negative 10x to the sixth power. So what do we have here? We have a negative lead coefficient and an even degree. A negative lead coefficient and an even degree. So negative lead coefficient and an even degree puts us in the lower left-hand box. And in that case, it's going to decrease both left and right. So we would describe that in behavior as decreases both left and right. And then we're also supposed to find the domain and range. Again, the domain of these power functions is going to be the same. It is going to be all real numbers. But with even degrees, since it is decreasing on both left and the right, that means it's not increasing forever. It's only decreasing forever. And in that case, the range is not going to be all real numbers. So let's look at what that function looks like. So this is what the graph looks like. It looks like a very flat, steepy, almost like a flat-ended parabola that's opening downward. It does have a vertex. It is right there at 0, 0. So notice that means that the y value is 0, but the rest of the graph is below that y value of 0. So that means that the range is going to be y is less than or equal to 0. Example 2 is going to have us to graph a power function and state its domain and range. Again, this lesson is going to be more about exploratory and how these graphs work. So you are going to be using a graphing calculator, which you can find at desmos.com, to do many of these graphs. So this one says pressure. For water to flow through a garden hose at a certain rate in gallons per minute, GPM, it needs to have a specific pressure in pounds per square inch, which is abbreviated PSI. Through testing and measurement, a company that produces garden hoses determines that the pressure P given the flow rate F is defined by P of F equals 3/2 F squared. Graph the function P of F and state the domain and range. We can actually graph this function without using Desmos because it is a quadratic equation, but I am going to go ahead and put this on a graphing calculator so you can see a very accurate representation of it. So let's go back to our graphing calculator. So there's that function, and just as we expected, it is a parabola, and this parabola has a vertex right there at 0, 0. And being a parabola and being a power function, it is going to have a domain of all real numbers. And the range, since it is only increasing to both sides and the lowest value of y is this 0 right there, the range is going to be y is greater than or equal to 0.